Okay, today in class we're talking about, what are we talking about? I forgot. Oh, properties of integrals. That's what we're talking about. Properties of the integral. Okay, so an integral, hopefully you remember, is the area underneath a curve between two given endpoints, or the limits of integration. So we're going to find, if this is our graph, it looks like a semicircle and a couple of lines that have the same slope. So it looks like this graph is pretty much an even function because it has y-axis symmetry. Okay, that might be good to know for later that this is an even function because it is symmetric about the y-axis. Okay, just notice that's going on. So we want the value from 0 to 3. 0 to 3. So we want to find the area underneath the curve of this graph and the positive x-axis between 0 and 3. Okay, so looking at this, I see three shapes. Hopefully you see two shapes also. There is a semi-quarter circle, right? This is a quarter circle. And then we have a rectangle and a triangle. So the area underneath the curve is literally the sum of these three geometric figures. So it's the sum of our quarter circle, so 1/4 of pi r squared, with a radius of 2. Okay, the radius is 2 from your center to your edge, plus our rectangle, which has a height of 1 and a width of 2, plus our triangle, which is 1/2 of base times height, 1/2 of 1 times 1. Okay, so there's a lot of these geometric things when we're trying to find the area underneath a curve if you don't given a function. So this is pi, because 1/4 of 4 is 1, plus 2 plus 1/2 is basically pi plus 2.5. So if you want to write 2.5, that's fine. If you want to write 2 1/2, if you want to write 5/2, all of those represent the same thing. So the second one says, what about from 0 to 4? Well, 0 to 4 is like we're adding on just one little piece over here, another extra triangle. So let's break this into the limit from 0 to 3 of our function. Okay, and then add in from 3 to 4. We're going to add in one extra piece than what we had before. Right, there's no need to do all the work all over again because we already know the limit from 0 to 3 from up above is pi plus 2.5. So we have to find the area underneath the curve from 3 to 4. Okay, so this one is another triangle. So 1/2 of the base of 1 and the height of -1 because it goes down. So in other words, we're going to have a -1/2 area that we add to our 2.5, and we have an area of pi plus 2 if we take the area from 0 to 4. Okay, so part of our properties of limits is that we can break this 0 to 4 into as many nice parts as we need to in order to make our algebra as simple as possible. Right? Math is hard enough as it is. There's no need to make it even harder. Okay, which moves up to our third one. What's the value from -3 to 3 of our same function? Well, from -3 to 3, remember this is an even function, or an even graph. So the whole entire thing is 2 times the interval from 0 to 3. Right? There's no need to do more work than we've already done. Because it's an even function, from -3 to 3 is the same as doubling 0 to 3. Okay, and since we've already done 0 to 3 at pi plus 2.5, let's just double that and get 2 pi plus 5 as the answer from -3 to +3. Okay, and these last two questions are kind of mind-boggling. So it tells us that some f of 0 of an original function is 5, and we want to find the value of f of 3, where f is the antiderivative of f of x. Okay, so if you think antiderivative, we're going to have to be thinking about the fundamental theorem of calculus. Okay, we're going to try and make an integral from our specific values. Okay, so I notice one of the values is 0. Wait, that's not what I wanted. I wanted to make it a highlighter. One of our x values is 0, and our other x value we're looking for is 3. Okay, so it might make some sense if we take the interval from 0 to 3. Right, of our function, and according to the fundamental theorem of calculus, that equals to the function evaluated at 3 minus the function evaluated at 0. Okay, so this is part of our one way to represent the fundamental theorem of calculus. F of 3 minus f of 0. And I have exactly what I want to solve for right here in my equation. I want to find f of 3. Here I have that as a quote-unquote variable. Right? I know f of 0 because they told it to me in the beginning of the problem. And now I just have to figure out what the area under the curve was from 0 to 3. And I believe I've already done that also. So we've calculated this up here in part 1. From 0 to 3, the area is pi plus 2.5. So this is pi plus 2.5. F of 3 is our quote-unquote variable, the thing we're trying to find the value of, the thing we're trying to solve for. And we were told in our problem that f of 0 was 5, so minus 5. Okay, so we make this equation using the fundamental theorem of calculus and replacing the things that we know. So this is a one-step process. We just simply have to add 5 to both sides. And I get pi plus 7.5 as the value of 3 from my function. Okay, so I'm applying the fundamental theorem of calculus in order to solve for the y value when x is 3 of a function that I don't have an equation for. So I have to use some other method, in this case the fundamental theorem. So our last question here is very similar to that one, right? We're given the y value for a specific x, and we want to find the y value for a different x. Okay, and of course it says where f is the antiderivative. So this means you need to think about the fundamental theorem of calculus and make a pretty equation that involves a specific integral. Okay, so the interval we want is from the lower x bound to the upper x bound, right? These are going to be your limits of integration from -2 to 2 of our function little f. And that equals, according to the fundamental theorem of calculus, capital F of 2 minus capital F of -2. And you can't see that because it ran off the page. This is -2. Okay? So there's a couple ways that we can calculate, right, this value from -2 to 2. That is going to be double, or in other words, it looks like it's a semicircle. Yes, if you go back and look at that, let's go up here and see. From -2 to 2, it is a rectangle at the bottom and a semicircle or a half of a circle at the top. So this is the area underneath the curve. That's how we're going to make this into a number. This is a half of a circle, so half of pi for pi 2 squared plus a rectangle of 4 units. Right, it's 4 units wide from -2 to 2, and it's 1 unit tall. So that's the area underneath my curve from -2 to 2, which turns out to be 2 pi plus 4. Okay, I'm trying to figure out what f of 2 is, so this becomes my variable, right? And of course that's in air quotes, my variable, minus f of -2, which my problem told me was -2. F of -2 is -2. So then this becomes a plus 2, so I will subtract 2 from both sides to solve this equation for f of 2. So 2 pi plus 2 is the y value from our function when x equals 2. Okay, so if we're ever given this antiderivative business, you need to know to make the fundamental theorem and find the area under the curve and solve for whatever variable you need. Okay, let's look at another example. This one's from an AP Cal test. from 2003. Let me take a picture. It'll be right here in a second. So here is this problem from 2003. This was number 4 on the FRQ portion, probably a non-calculator portion, I would think, because you really don't need a calculator for any of this. Okay, so we have a continuous function on a closed interval with f of 0 equals 3. Okay, these are the graphs of f prime, the derivative, and is one line segment in a semicircle. Okay, so we can assume that this is a nice smooth semicircle. We can calculate its equation if you want to, but it's probably not necessary. Okay, on what intervals is f increasing? Okay, so if you think about your f and f prime and f double prime connection, f is increasing when the derivative is greater than 0. So we are looking for where is this graph, which is f prime, where is this graph above the x-axis? And it looks like that place is only occurring between -3 and 2. Okay, so this is our justifying that because f prime is positive, right, on the interval from -3 to -2, right, we're going to use open intervals because it's not doing anything at a dot or at 0. So the open interval from -3 to 2, f is increasing on that interval. Okay, so we have to make a connection between f and f prime. Okay, when your derivative is positive, your function is increasing. And when your derivative is negative, your function is decreasing. Okay, find the x-coordinate of each point of inflection of the graph on the open interval from -3 to 4. Okay, so in points of inflection means that your second derivative changes signs. Okay, when your second derivative changes signs from positive to negative, that is when we're going to have a point of inflection. Okay, so we don't have the graph of the second derivative at all, do we? We have the graph of f prime, the first derivative. So we need to figure out where is there a max or a min.
Wait, is this supposed to be f double prime?
Okay, so let's do ourselves a little sign analysis of the zeros of your function. Okay, so here the derivative is undefined, right? So at 0 we're going to have an undefined value. Okay, probably an asymptote here. At +2, right, we have a local max. And at 4 we have an endpoint. So that's right, it's on the open interval. So it looks like if we're between, here we have increasing values. So we have positive between 0 and 2 and decreasing values from +2 to +4. So at x equals +2, there's going to be a maximum value, and you see that the sign changes from plus to minus. Okay, so we're going to have a point of inflection at x equals 2 because the derivative changes, the second derivative changes from positive to negative. So where f would be concave up here and f would be concave down, right? Not f prime. These are graphs of f prime, so we're not talking about what that graph is doing. We're making inferences about the graph of f. Okay, part C says write an equation for the line tangent to the point at 0, 3. Well, that's good. We've already been given the point on the tangent, right, 0, 3. So we basically only need to find the slope of our line at 0. So to find the slope of the line at 0, we go to our graph and pick out the y value. What is the y value when x is 0? It's -2, right? This is the graph of the slopes of our function f. So we have a slope of -2. So y minus 3 equals -2 times x plus 0. Or maybe we should put -0 since that's kind of what the equation says. Okay, you don't have to simplify in calculus. Now, here's the part that we're working on. Find f of -3 and f of 4. Okay, so we want to make an interval, probably from -3 to 0, so that we can figure out what's going to go on here. of our function f prime of x dx, and that's equal to f of 0 minus f of negative 3. Okay, we're using the fundamental theorem of calculus, creating our very own limit of integration so that we can have f of 3, right, somewhere in our equation. Okay, so this is the area under the curve from negative 3 to 0. So from negative 3 to 0, that area is going to be a triangle. Right, so we have 1/2 of 1 times 1 minus 1/2 of 2 times 2. Okay, and f of 0, we're told, where are we told this? We're told in our problem up here that f of 0 equals 3. Okay, so f of 0 equals 3 minus f of negative 3. So this is negative 1 or positive 1/2, right? That's the area above the curve. And we're going to minus 2. That's the area of the triangle below the curve, right? It's negative because it's below the curve. Negative 2. So this is negative 1.5 equals 3 minus our f of negative 3. So we subtract 3 from both sides, equals negative f of negative 3. So it looks like f of negative 3 is positive 4.5. Okay, we would do a very similar thing in order to figure out what the f of 4 is. Okay, we would pick an interval, probably from 0 to 4, of our f prime graph, since we have f prime, and then the antiderivative of f prime is, of course, f minus f of 0, and this would allow us to figure out what your f of 4 is. Something like that. So this is a semicircle. Like this, actually, it would be negative, right? So negative 16 plus, I guess that would make this a negative 13. Sorry, I did some poor algebra in here. Let me erase this. Negative 13 plus 2 pi. Oh, that's the bell. So, gotta go. Hopefully this was helpful, and we'll see you next time. Bye.